Fix for a single CPU first, resolve the TLB miss problems, resolve the secondary mission problems before you deal with false cache sharing and barrier synchronization problems. Okay, fix these issues first.
Can you repeat again what the cache busting is?
Cache busting is where my data is larger than my cache. So code 2, for example, is a 22 meg program on an 8 meg or 4 meg secondary cache. So my data set is bigger than I can hold in a single piece of secondary cache. That would be like taking the weather model that was at a 100-mile grid, and now I'm going to go to a 1-mile grid. At some point I bust that secondary cache. It worked when it was small, but it didn't behave the same as it got bigger. And that's where the Cray market has always been, is again, try to get the benchmarker to up the detail of the problem, and eventually the vector type machine will outshine the cache machine because we can bust the cache. Crays were always designed for the large problems that they're trying to solve. Oil reservoir modeling from blast data blowing off dynamite and figuring out what's the ground look like underneath, stuff like that. So cache busting was my data set's bigger than the secondary cache.
And the straight,
How I go through the data. If it's a three-dimensional array, or if it's vector arranged versus cache arranged. C and Fortran arrange their arrays differently. One's what they call columns, and one's what they call rows, and that results in the way the array visually looks being placed in memory in a different way. And origins are really more designed for C than Fortran, cache-based machines in general, because of the way the data is laid out.
Can you repeat the cache stride?
Cache strides is how I go through the data. I can sequentially stride through the data like an FFT program. I've got all this frequency data and I'm running it through an algorithm in sequential data. Nastran, for example, vibrating cars is modal analysis. So my data set is a contiguous stream of data. Okay, so I'm sequentially going through, my reads and writes are sequentially going through it. But maybe I've got a three-dimensional array, so I've got dimension X, dimension Y, dimension Z, and then I end up bouncing between them, depending upon how I overlaid my, or nested my loops and stuff. Okay. Or that could be a sequential thing of how I stride it, or the other thing might be gather scatter, where I pull a bunch of numbers and those numbers tell me where to get my data. Okay. So those are two different scenarios: sequential strides with multi-dimensional arrays, or gather scatter. So for these, I'm going to point you to a book. I may as well do that right now. And then we should take a break here. Off on Tech Pubs. So this is available to customers in a standard location. I go to 6.5, actually the developer toolkit, developer list of books, and I want to go under O for Origin Optimization Tuning Guide. So this is outside the firewall, and here's the manual. They're calling it right now still the Origin IRIX Performance Tuning Optimization Guide. So for the programmer that has control of the source and can rewrite the Fortran or the C, this is the manual that I would put them to that talks about busting strides. Now they call all of these cache thrashes. All four of these effects will just mix together as cache thrashing. But I'm saying there are 4 different reasons for the thrashing effect. So that's available outside just the Performance Tuning Optimization Guide. And it applies to the Origin 3000 as well. No big difference. So tune for single CPU first, and the biggest thing is modify the code for better cache utilization, and that's exactly what we were just talking about, the stride issues and stuff. If I go back to this manual, I'm just going to click into it, the table of contents. It also talks about TLB misses. What did I click on? Wrong one. So this optimization guide has a chapter here on optimizing cache utilization. And in here, it's got reversing loop nesting and things like that to achieve various stride patterns through the data. And understanding, they're just calling it, lumping it together as cache thrashing. And then they're just talking about how the data is being laid out in memory and stuff like that. And they're just going through a three-dimensional array example that they have, where they have to go through 3 dimensions. And this is X, Y, Z, and during Z sweep, they've got the Z dimension they're going through. And then they suggest options for that. Copy to circumvent TLB misses. Copy the Z array small enough to avoid thrashing. Carry out a Z sweep on a scratch array and then copy the results back. Break it up into pieces, go through it, and then put it back together. Or larger pages. And then for the cache misses, so this is the actual chapter talking about how to rearrange my data, going to large pages. And now for the cache busting and cache stride issues, again, they're showing a 2-dimensional array here. And talk about cache blocking, loop fusion, and they go through an FFT example as well. Okay. I don't want to spend any more time on this. Let's take our morning break here. And hopefully, let's see if my jobs came back. Yeah, I've got some reports now. Okay, good. So let's take a 15-minute break. That kind of puts us at about 20 after 10.
Do you think that to do this kind of stuff, like performing, tuning, and and this kind of stuff, it would really help if you know C or C++ or Fortran?
It helps a little bit, but in a lot of cases, the system administrators don't have the programming background.
Right, because you know what, I feel like I don't know C or C++. I have programming in Java, but I had never used C or C++. So there is sometimes that I feel like I'm missing one thing, and I just wonder if I start learning C, it's gonna help me to do this better. You know what I mean?
I don't think that'll help. Really, it's just a matter of getting involved and doing it and getting exposed to lots of different cases.
Oh, really?
Yeah. I'm not a C programmer. I mean, I modify C and hack around in it, but I don't start from scratch and create this C product or anything like that. So you can get into C and Fortran, but that for a system tuner, there's a point where they don't care about that. They simply tell the programmer, this is what I'm seeing. Okay, so that's where we are right now. So we're going to look at the profile reports and then see what's going on with Pro2. What is it spending its service time on? But everything I'm doing is looking at SAR and accounting data, figure out what application to look at, and then try to figure out does it have any of these problems. Okay. And then at some point you can direct them to that tuning guide I showed you to deal with caches, barrier problems, and stuff like that.
And that's something that the programmer needs to know how to do it, to deal with that. You just point where the problem is.
Right.
Okay.
And then let them worry about it from that point on.
Okay.
So we're in the process of tuning for a single CPU first, and most of what we're doing is compiler optimization, loop nest, the way the loops are nested and stuff like that. Question, yeah.
Well, big difference between the O3 and the MP usage.
Yeah, we're going to see that. So he's running the multi-threaded version now. That's fine. That's what I'd asked you to do yesterday. Now, this modifying code utilization issue. This is a NUMA machine, meaning that I've got different latencies to different parts of my memories. But the purpose of a cache is to hide that. If I don't modify my code and it's still abusing cache, then my data distribution is going to be very, very critical. but you want to fit it into cache first, and that will hide a lot of the memory latency. So in my particular case, I can't get code 2 to vary more than 1/10 of a second by how my data is placed. So I'm just trying to say that the cache utilization of the program is much more important than the data distribution issue. Okay? Because the purpose of the secondary cache is to hide the memory latency. It's only when I miss secondary cache that I have to see memory latency. So if I got the data in cache, I don't see memory latency. That's the whole purpose of the cache. Unless I'm missing cache because of busts or strides or system cache crash. So they've got distributed data here. There are two sides of the story here. Am I single-threaded or multi-threaded? If I have a single-threaded 1 gig job, I want to distribute my pages round robin across all the nodes so that I've got more than one page coming in at a time. So in my example, we've got a 8-node system for do, which means I could have 8 separate pages coming in from 8 separate memory ports to these 8 separate nodes' memories. And that's going to be a bigger bandwidth than just going off to one memory and grabbing through one memory port the data that I need. So single-threaded large memory jobs are better off round-robin distribution. Whereas once I start multi-threading, when I'm multi-threading, I'm breaking my data up into pieces, and hopefully I'm breaking it up into pieces small enough such that it fits into my secondary cache. Then, again, locality is going to be much more important. So in a multi-threaded situation, I'd rather have first touch or placement close to me. So as I'm processing my data is in my own node board, and the data that another CPU is working on is in its node board. So single-threaded large and multi-threaded are two different decisions that you have to make. But the data distribution is not going to be as critical if you're satisfying everything out of cache and you've taken that loop that was designed for a vector machine and now written it for a cache-based machine.
So, is this a single thread you wanted to distribute in different nodes?
There are compiler directives to say put this piece in these locations, or at the command line level with dplace.
Okay.
So I can say dplace and then tell it put page addresses these on node 0, put these addresses on node 4, and I can decide where I want. I can decide which CPUs and what memory pages I want to be placed where.
Okay. I mean, in multi-thread, you want it just in one place, in one node.
Well, in a multi-threaded situation, each thread's going to have its own CPU.
Okay.
So I'm saying in a single-threaded situation, I want my large memory stuff spread all over so that I can get more of them coming in at once. But once I multi-thread, I don't have data such that it's spread across all the nodes. I'm better off staying just on my own node.
So you want your data where the CPU you're using for?
Correct.
Okay.
But if I can't get it all in my local memory, I'm better off round-robining it.
Okay.
So if I'm going to bust my memory, let's spread those pages across my nodes. Because I can get more data in, more bandwidth to it. So in a compute server, a job mix server, you're better off leaving this stuff alone and fixing it on a per application basis, because some applications will benefit and some might actually not benefit. We're going to talk a little bit about modifying code for better I/O. This is deciding whether I'm going to go through cache or do direct, what my buffer sizes are going to be like, things like that. And then multitasking, multi-threading the application. And the last thing I worry about is getting the right answers. Anyway, real quickly, the compiler has a couple of options to decide what microprocessor you're using. And sometimes there are older built binaries. For example, a -32 might still exist out there for compatibility reasons. So that the vendor can support the same source for both an IRIX Indy 32-bit or an Origin product line. And they don't want to go into two separate source trees or separate binaries for these different platforms. So they're trading portability for performance, or I should say giving up performance for portability reasons. And there is the ability on the newer systems to go to a 64-bit binary addressing scheme within the binary. There's a little bit about this now on the next page. So N32 over an N32, over just a 32, takes better advantage of the architecture. tells the compilers I've got more floating point registers. It tells the compiler my integers are now 64-bit, so I won't truncate or overflow as easy. And there's a couple other registers that are available to you. So the key difference between N32 and N64 is the size of the pointers and the integers. Now they recommend here 64 to be used only if my application needs a certain amount of address space. A lot of the vendors that I'm talking to are going to dash 64 now so that they can debug 64-bit binary problems before it's a commercial product. So they're taking a trade-off. Dash 64 will make your binary bigger. Not much, and that's what the developers are saying is the larger size isn't as bad as the debugging 64-bit issue. They also know that their vendors or their customers are going to get into larger data sets. So they're trying to make sure with 64-bit addressing that I can deal with larger arrays and stuff. So some people may say avoid dash 64, in other words, others are doing it just to get it done with. Okay. So with an N32 you get smaller executables. That means fewer cache misses and less memory paging. Because you're now taking 32 bits instead of 64 bits for memory addressing and for integers and stuff like that. Now if you do an N32, you can still get 64-bit integers going long int 8. Those are two different ways you can declare within your program to say make this a 64-bit integer. Again, the only thing we're concerned about right now on this page is 03, which is going to my most aggressive optimization. And maybe I should just check this now by telling it to do. Run ACCOM. ACCOM-N, code 203. So nothing in there. Which means it's probably switched, so I'm doing var ADM PAC asterisk. So I've had 3 code 203s running. I was hoping other people would be running them too.
They're running right now.
Okay, they're still running. So in my example, I don't have enough of a sample yet, but I had those 3 that I ran before a break, and we are now down in the 290-second range. From 2000, that 03 brought me to 290. Significant speed up. The other codes will not experience the same speed up because of the way their loops are nested and stuff.
Check MP.
Sure.
See what it's running at.
It's fine.
One of the graphs made it look like it was running faster than that one.
It's possible.
So how you did it to run, what you did it to the system that it went from 2000 seconds to 290?
That was the 03 option. That's right where we are. So I was saying the 03 is what I did this morning. So the compiler was able to better utilize cache and to nest my loops and do a few other things to optimize how instructions are organized and things like that. So there's a whole bunch of things that 03 did. Loop nest optimization was one of them. When you actually run it with the dash show option, the 03 will then show you what you're actually getting. Hang on a second here.
how did you run it with the 03 option?
The jobs already have them set.
Oh, you're setting on your program.
Yeah.
Oh, okay.
So in this case, and again, I didn't check status. I'm responding to his question right now, looking at the 02 MP versions. And there are some 17X statuses in there. So some of them are dying. It looks like your 8Y, 1, 2, 3, 4, 5, 6, 7, 8. So signal 17. It looks like they're not running successfully. SIG user 2, which is probably coming from NQE, they may be hitting an NQE limit. Okay. That doesn't look too bad. So we'll have to see what happens there. So, in answer to your question, We used a .-03 on the job.
Oh,
And that,
okay.
the original ones, take a look at code 2.nqs, and that's why I'm compiling in each run.
Alright.
So here, I just did a show, but there was no options on it. It was a default compiler. And then code 203.nqs, I then added a -03 on it, and I also named the binary 03 so I could spot the difference between them. Now I could also look at the compiler set that I'm using and go to a different compiler as well. Go to a newer compiler, for example, newer libraries, but I'm not going to at this point until I start seeing a problem. I'm going to have to take a look at that code 2MP to find out why it was dying, but the SIG user 2 was coming from the NQS daemon more than likely. So I was thinking it was doing something.
When you switch, there is any limitation, like when you are in 32 or 64 compiler, like I have this client that they have a limitation on the amount of memory they want to
Right.
allocate. I remember they say, well, I have 4 gigabytes of memory, and with malloc or calloc, I believe, he couldn't allocate more than 2 gigabytes.
Right.
So his question was why I can't allocate so, and
You need
finally,
to go past 2 gig, you need to be able to have 64 bits to describe the address of it.
oh really?
Yeah. So that's what I was saying here. The -64, if you need a certain amount of memory, now this was saying 4 gig, and I think you're right on 2 gig. I'm not sure where the 4 came from.
Yeah, 32 bit can only go up to 2 gig.
Right.
Okay.
So if I need more address space than that, I need enough bits, or I'm going to truncate on 32 bits. So -64 did 2 things. It changed my addressing
Okay.
for the array from 32 bits to 64 bits. And that's again the reason that a lot of these customers are going to 64 bits right now, just to get a -64 to start debugging and getting their codes running in that mode. And some of them are still running N32 just because they don't have the resources to rewrite and certify and go through the rigmarole of making sure the application will work by the time it's released.
Okay.
But the second thing you get besides the larger addressing space is the integers. A long int would overflow on 32 bits, and then you start getting bad numbers again, and you start going to 64. And a lot of times when you overflow, they go into super big numbers or something like that. They're way out of range numbers.
All right. I'm sorry that
That's okay.
you have to get back.
So the 03 was the biggest speed up for us. I'm going to also try running codes 1, 2, and 4. Q sub code 1, 03.nqs.
I ran all those codes just yesterday afternoon before we left.
Good.
So they're in yesterday's
Yeah.
list.
So they'll be there, and again, I'm just trying to run enough of them to get this sample of the spread of the numbers. What range do I have? Because they could be coming in at any different range. And if I bring up top now, you can see the codes running there. Account-n. So here's a code 103, it now went down to 25 seconds. From 66 seconds to 25 seconds, which is only a third of it. We got a lot more out of code 2. We probably got 10% or 2,290. Yeah. And we'll wait for code 3 and 4 to come back too.
I guess that option must be probably documented in the actual
Yeah.
compilers.
Sure, and on the man page and stuff.
Oh, okay.
And again, we're really not interested in application tuning, I'm just showing the hot buttons that would be relevant to us here at the command line level.
33 for 60.
Yeah. 25 still, 33 was the elapsed, which included IO8 and stuff.
That's waiting. Code 1 and code 3 both basically.
Got about the same speed up, roughly, this one's a little bit slowed down. And note that the memory sizes are still about the same. We didn't look at I/O in this example, but the I/O is going to be the same too. So code 3 is still about 3 meg. Code 1 was about 17 meg. I had 16 meg up there. It got just a little bit bigger maybe. And we're still waiting for code 4. Anyway, while we wait for that code 4. So there is the ability to mess around with compiler defaults, but I generally don't advise it because then every application picks up those defaults. You're better off changing it on a per compilation basis, on a per application basis. So something I do in here might help one application and hurt everything else. Again, what I've been doing is use a dash show on my compiler line. So when I go and take a look at one of these reports, I can see exactly what the compiler options were. I'm going to pick 391 here. So with the dash show, I can see all this sort of stuff that was going on. So I can see in this case, I was still in N32. I was not going to dash 64 here. I was a MIPS 4 R10K binary instruction set. There's the dash 03 binary. And some of the other arguments that seem to get echoed and passed off to these particular commands or include paths. Here's more of the compiler work. All these defines that are going on in here. That's all compilation stuff. I still see N32. I still see the dash 03. So I see all the different arguments that are being passed to the compiler. So those are on the man page. So this is what show is giving me. And I've got a slowdown going on right now. Slowly but tolerable. I'm going to do a quick SAR command. Now this may be after the event, but I've got both file system buffer cache and swap going on. My machine is I/O bound right now. So 56% of my time I've got processes waiting on I/O. And most of that is waiting on file system buffer cache, a little bit waiting on the swap device. So the slowdown that I've been experiencing in my mind is still mostly the file system buffer cache. And we're going to learn how to tune that Thursday. And my user time is still in the 40%, my system time's real low. So most of it is over half the time I've got stuff waiting on I/O, and most of that is waiting on buffer cache I/O. And so I was just responding to that event. Let's see if we still have ACCON data. There's a code 403 is now at 165 seconds. So I saved about 35 seconds here, 35 seconds here, 1,700 seconds here, and 200 seconds here. But they're all a little bit different, depending upon the algorithm that they have in them. So I just finished looking at dash show, and that's why in my job runs I'm doing a compile and a link so that I can compare what the job was built like, go back and see the compiler paths and all that sort of thing. Anyway, so we're at SpeechShop. SpeechShop has a variety of different experiments. The only one I'm interested in right now is user time. And the second one we're going to talk about is hardware counter profiling. So once I've got my top applications, again I'm going to do my SS run dash user time, which will give me the top subroutines of my program where I'm spending all my time. Then I'm going to do a perfx dash AY to figure out what hardware events are occurring during my CPU service time. Then I'm going to go back to SS run and use a HWC counter to say now trap on the counter that is biggest. For example, TLB misses. Find out where in my program am I taking all my TLB misses. Now, SpeechShop doesn't require any special compilation or relinking. It will link in all the appropriate libraries. There are two types of ways that SpeechShop looks at things. One is called Pixie, and one is called profiling. With Pixie, I actually link in additional code into each subroutine and count the number of times I go through the subroutine. So this is called block counting. And that's, by the way, a dash ideal experiment. So the dash ideal experiment is basically adding code into my program to count the number of times I go through everything. That's going to slow down the program. So every time I go through a subroutine, I execute additional instructions I didn't before. That's what Pixie does, is stick in those additional instructions. Again, this is also called block counting. So I'm counting the number of times I go through a block. The second way is a system call. So my system time can start going up as I make these profile system calls, and that's asking the kernel, look at my program stack. Okay, that way we can characterize what's going on with my program stack. So this is where we get into program counter sampling. I say, where is my program counter all the time? Every time I look, what's the address that it's at? And then user time is tracking, where am I spending all my time? What subroutines is all my time spent in? And then hardware counter profile, I'm going to say, once I know that a subroutine is spending all of its time in TLB Misses, then I can track on the TLB Misses and find out where I am. And heap tracing is for memory mallocs. So if I want to track, in the case of the memory leak, I can do an SS run heap experiment and then see how my mallocs are growing and shrinking and stuff. So maybe somebody has a library routine they created that did a malloc, and then you were supposed to unmalloc later by calling a close down routine, but the programmer didn't. So they keep getting the mallocs, but they never call the unmalloc piece. So the first one was programmer counter sampling. I kind of switched them in the order here. But profiling here, we pull the program counter periodically to figure out where it is. And that's going to include all your user time, your CPU time, your memory reference time, execution of your user code, execution of the system code, so you'd be able to look at this, for example, is the fork system call, the create processes, context switching, doing reads and writes, floating point errors, general interrupts due to disk interrupts or network interrupts. They're kicking you out of the CPU. So program counter sampling is a system call interface. In this example, they did SS run, name of the experiment, F standing for a fine programmer counter sampler. And in this case, they're sampling every millisecond. So every millisecond, the libraries make a call to the kernel to say, what's my profile information look like? So they do SS run, name of the experiment, name of the program, and any sort of command line arguments the program would have. And then to view it is the prof command. So SS run collects the data, and then you run prof on the name of the command dot name of the experiment dot PID. So every process that ran in that experiment is going to have a dot PID file associated with it. So in this profile report, I see that I looked at the program. It ran for, it looks like, 11 seconds. And again down here, I see that the time was 11 seconds. It was R10K at 194 megahertz, one CPU, and every millisecond that I looked, I got 11,436 samples, which comes out to 11.43 seconds. And what we have here, 10.93, so there's a slight difference between the two. Okay. So, looking at those 11,436 seconds, we figured out, when I looked, where was I? And at the top of the list, 9,508 times Csuite was where I was, and that accounted for 9.5 seconds of my 11 seconds that's tracking here. And then I see X sweep and Y sweep, which are very, very small compared to the initial 9.5 seconds. So in going to this, I would then be looking at Z sweep as the subroutine where I'm spending all my time. 83% of my time is spent in that subroutine. Okay. Now the next thing I need to do is look at perfect to figure out what's my hardware events. And if I had my way, I would get Perfect's data just for Z Suite. But you have to rewrite your program to do that. And I don't want to do that. I can't. So I'm going to run under Perfect's and collect that same sort of data. Okay.
How did you load your, when you run the prof IDE to the SPC and you say the last thing is the PID?
Right.
How'd you get that?
They didn't show it here, but in LS or something like that.
Oh, okay, so you have to do like
Yeah.
PS minus
Yeah.
EF or something to find it.
Or there are no files there when you started the experiment, and when you're done, you can see what they were assigned with an LS. But you're right, it doesn't show that here, what the PID was, but in this case, they stuck it in and they cut out the piece that showed how they found that. That's a good point. Now, I'll show you what I'm doing in our jobs, but I'm using a wildcard, so I'm doing an asterisk for that in piece. But again, I'm running in a unique directory with a batch interface, so there's nothing else in that directory. We'll come back to that. So the second piece then was pixifying, which is block counting. So we count the number of instructions in a block. A block is basically labels, jumps, and branches, a subroutine. Entry point and exit points from a subroutine. So it counts only instructions executed in user mode. We cannot count what's going on in the system routines because we cannot pixify the kernel. And it doesn't include memory access time or instruction decode time, and it kind of assumes a perfect memory system. None of the tools can really account for NUMA. They're just doing an approximation of what they think the memory loads are costing me. So to do a pixified block counting, they did ssrun-ideal. And again, they missed showing it here, but they then did a prof on it, star ideal, and then whatever that PID was. And now it's counting the number for each subroutines, number of cycles, how many times I call myself, children, and a ratio of called versus total. Again, here's Z Suite down in here. It wasn't counted as different, but it spent a lot more time. So in this example, X, Y, and Z are all called the same number of times. But remember from the earlier sample, the time spent was all in Z Suite. So the fact that Z Suite is showing more than the other routines, I really want to get Perfect's data on Z Suite compared to the other two. But I don't have that option here. I'm just going to run it as a child of Perfect's for the whole application. Now here's the one that we were doing as user time. So in this example, ssrun user time ADI2, then did a prof on it. And then we see the total time in this case was 12.57 seconds. Now we only looked 419 times because our sample interval is 30 milliseconds, whereas before it was a 1 millisecond sample. When I did the FPC, the fine program counter sampling. So this is 30 millisecond samples. So that's going to be less system time. The other experiment would have had more system time because I'm making system calls every millisecond. So this is 30 times slower on my system call intensity than the other one. And then again, I see what percentage of samples, but again, for myself, all the time is being spent right here, 10.29 seconds in Z Suite. 343 of the total 419 times Z Suite was in the list. So Z Suite is what I'm interested in this example, which happens to be a third dimension that we're striding through, and the TLB misses are what are dominating it. And going to larger page sizes might help in this example. Now I'm going to skip over a couple of things and go to my program counters. Then I'll come back. $735. Okay. We have 32 hardware counters on the chip. Every time I decode an instruction, I increment a counter. Every time I do something, I increment one of these counters. This is built into the chip, the hardware. Many of chips also have hardware counters, and you can get to these statistics in Linux with a Perfect's command there as well. Now the -A option says look at all 32 at once. So we're going to multiplex. We only have 2 ports to read the counters. We can only read 2 counters at a time. So if my process is only a tenth of a second, I could have large variance in the numbers that I get. But I'm using an A and looking at all my counters. And X says count the kernel mode too. Without X, I would be missing time. For example, TLB misses. If I don't use the dash X, then TLB misses will not show up in the report because that's a hot path into the kernel. So I always want the X option. And then the Y option is getting me this report format. Now what we're really doing is we've got these counters. So this is what came off the chip. And here we've got this large 193.828.01144 number. That's the number of times while I was connected to the CPU that I executed the clock period. And event numbers 0 and 16 are the exact same counter, the number of clock periods or the number of cycles to my program. And this is just user time. So in this example, they take those clocks and convert them into a time. And this program looks like it took 9.889 seconds to run. But again, if I had left X off, it could have been quite a bit different. Now, because this machine can stack instructions and overlay and interlock and change out of order instruction execution, we have a min and a max and a typical. So what there is a cost table that's written. The cost table says for every one of these events, give me an average, and give me what the smallest might be, and also what the worst case might be. In fact, usually floating point, there we are, floating point instructions, in this case, 7.69 seconds, because floating points are the most complicated. They've got the most number of clock periods that they've got to issue instructions. So we're just taking these hardware counters and converting them into an approximate, what I would consider a fair typical number. That's the number that I'm always using. And then the other two just give you a range of saying this is the range that it could have been in based upon what my overlaying of instructions can do. Okay. So there's actually a cost table that does this conversion. And some of the newer systems, that cost table has been screwed up. So you got to be real careful about it. In fact, I was going to check the SN1 system to see what it's doing. So on this report, we got the event number, the event name, the actual counter that came out of the kernel, and then what we would think that would cost me in seconds. So we say a floating point instruction takes 9 clock periods. So we then take that counter number, multiply times 9, and also a min and a max range. Now again, remember what I said yesterday. We have issued instructions and we have graduated instructions. An issued instruction says that it started, a graduated instruction says that it finished and was used. And I've got a speculative chip here that may say, because of my branching, I'm going to start that instruction decode, but then I hit the end of my loop, and my speculation is no longer true, and the instruction that's been put into the decode pipe is now thrown away and does not graduate. Also, we could have graduate or issued larger than graduated if I don't count prefetch operations and stuff like that properly. So there's issued and there's graduated. Now, there's 32 counters here. Let's just go through the ones that are going to show up with my FX. So TLB misses. What is the event number for a TLB miss? TLB misses right here is event number 23. So if that's at the top of my list, then I'm concerned about it. Now in this case, it's only 1.9 seconds of my 9.8. So I might not be too concerned about it, but that is event number 23. So if I see 23 at the top of my list, then I want to talk about reorganizing my data or going to larger page sizes, things to reduce my TLB misses. So if I've got an 800-second process, and this shows it's all TLB misses, if I can get those TLB misses down, my 800 seconds may get shorter. Secondary data cache misses. There are 2 associated with that one. So I'm just going down the list. The first one is event number 26. So every time I miss secondary cache, I have to go off and get the data from memory again. And event number 26 is what did that. But the actual data movement is also counted in here Event number 7 is quad words moved to secondary cache. So these two go together. 26 and 7 are used together. One is the miss and one is the data movement cost, how much it took in time to move my data. Now, multi-threaded barrier synchronization is done through memory. So if I know that I'm multi-threaded, the event number that's going to be showing up are loads, branches, and stores. And I'm going to come back to this a little bit later. Depends upon how we do our barrier synchronization. But just to be sure, let's cover them all. So loads are 2 and 18. This was my loads. So basically we have this barrier region in memory that tells me what the other CPUs are doing or what the other threads are doing. And I keep loading that barrier bit and checking it to say, are you there? Are you there? Are you done? Are you done? That sort of concept. By the way, on the Cray world, we had deadlock interrupts to take care of that. And in SN1, they did add hardware support for deadlock interrupts between CPUs, but the MP libraries are not using that yet. Once they use that, if I can convince them to do that, then barrier synchronization would show up differently. So if I have a program, remember I said code 2 took 2 weeks one point. I waited 2 weeks and at the top of the list was loads. So the loads are saying, read the barrier bit, read the barrier bit, read the barrier bit. Are you done? Are you done? Are you done? Each time. Now the other 2 events will depend upon how I've set up environment variables. But I may have a branch with it as well. So I read the barrier bit in branch, but I can hide the branch with a different type of hardware mechanism. And I want to come back to that. So the branches were events number, where are we? Decoded branches, event number 6. And in the latest compiler version, not the older ones, but in the latest ones, we also now have stores going on. And I believe it's reading the barrier bit and then storing some information like how many times did I try the barrier region. That's what I'm assuming. I've not looked at the code. So in the newer ones, I have stores that might be there too. And these 3 will be all tightly knit at the top of the report. So the stores were 3 and 19. So we've got now 1, 2, 3, 4, 5, 6, 7, 8 of our 32 counters. 9 and 10, clock periods, just total number of clock periods for the program. So that's 10 of our 32 counters. We also have things like primary data cache misses, quad words moved to primary data cache. I'm not going to talk about them here because that's application tuning. We've got the loads, the branches, the stores. Event 21 is the good one. Event 21 for us is our floating point computation. So code 2, I'd like to see 21 at the top of the list. That says I'm getting the most work done. There's a store prefetch exclusive to a clean block in secondary cache. It means I wrote to a clean block that is not shared, it's exclusively to mine, that's in secondary cache. So it means I modified a write variable, but nobody else was using it. Okay. The one that I'm more interested in is down here, a couple more. 31 says I wrote exclusive to a shared block in secondary cache. So the shared block in secondary cache is an indication of false cache sharing. And that was event 31. So if I have event 31 showing up down here, as the number of threads go up, event 31 also goes up. So as my threads go wider and wider, I get more of these storing to a shared cache line. And what happens then is the event 31 says, I just did a store. So then we get these other counters going, external intervention and external invalidation. So 28 and 29 then happen because of event 31. So 28 and 29 will be going up with event 31 as my thread width goes up. So it all starts with an event 31. Event 31 causes a 28 and a 29 to go up, which causes 26 and 27 to go up. They'll all go up together, particularly as I go wider thread width. Most of these others I don't really care about. Mispredicted branches, instruction cache misses. Event 31 is a very important one. Again, with event 31, if that's what started my false cache sharing, then when I do this SS run on the hardware counters, the counter I want to trap on is event 31. And that would tell me where am I in my program when I wrote to a cache line that was being shared by everybody. So the developer has to trap up 31 and say, where am I every time I write to a shared cache line? And then they can get into padding the variables or something like that. What else did we have here? Secondary instruction cache misses. There is a command called chord that allows you to reorganize your subroutines so that they're closely packed by common use. Instructions, issued instructions, don't care about. Errors, any error, ECC errors, don't care about. Instruction misprediction. Note that most of these, even though they have high counts, have no cost in time. They're coming up 0 here because they occur, but they result in the time showing up in quad words moved to secondary cache or something like that. Not sure we care about any of the others. Graduated stores, data misprediction. Don't really care about any of the others. Also, by the way, then at the bottom, so this is giving me the hardware counter. During that 9 seconds, 2.5 was spent on secondary cache misses, 2 seconds was spent on TLB misses, 1.5 seconds spent on moving data to secondary cache. So all of that is data arrangement. All the data is arranged in memory. And then after that, everything else is pretty small. Primary data cache misses a second, and it pretty much trickles off after that. Let's take a look at our code. I'm going to pick the latest one here. Profile report first. And I don't care a whole lot in this report. I see the compile working, and here's my perfx report, or my